Makespan in precedence constraints.
Okay, thanks a lot. Yeah, I know it's the talk after lunch, so I hope you got enough coffee, and we'll see that this is going to be some light entertainment, I hope. Okay, so this is some joint work with my former graduate student, Elaine Levy. Okay, so this is about one of the classical problems in scheduling. And here we go. We have a set of n jobs, j, and first of all, things look easy in the sense that they all have the same running time of 1. So these are unit processing time jobs. And I have some number m of machines, and they're all identical. The only thing that makes the problem nasty is that I have precedence constraints. So this is indicated like this. So it means that job indexed by 1 has to finish before I can start with job number 3. And my objective function is I want to schedule the jobs on those m machines so that the make span, the time that the last job finishes, is minimized. This is one example solution. I think this is the optimum solution. So this is a schedule of my 13 jobs so that the make span, the time that the last job finishes, is minimized. And you can see that I hope I didn't screw up. For example, if you look at job 1 and job 4, there's a precedence constraint, and indeed job 4 starts only after job 1 is finished. Okay. So to warm up, let me show you a 2 approximation that's known since the 60s, and this is due to Graham. And the algorithm is as easy as it could be. You just do everything discretely. So you do the following. You look at the first time unit, and you stare at your jobs, and you look at which job could you possibly run at the first time unit. There's job 1, who doesn't have any precedence constraints incoming, and job 9 doesn't have any incoming precedence constraints. Then you stare a little longer at your jobs, but now you see that actually all the other jobs, they depend either on 1 or 9. So I leave this the last slot empty, and I just go to the next time. And I schedule maybe job 2 and so on. And you see, you just do everything greedily, and so until you're done. If you look at this, then you see that we didn't do things optimally. This is the same instance as on the last slide, and there is this long chain here. And I probably should have started with that one earlier. So it's kind of the greedy algorithm didn't see that coming. Okay, so now why is this a 2 approximation? Okay, so let's stare at the last job that got finished, and let's wonder why didn't we schedule this one earlier? So in particular, let's look at a time unit where we had 1 slot idle, like here. Then actually this job must be dependent on some job scheduled at that time. And now you wonder, why did I not schedule this guy earlier? Well, I look at the last time unit where I didn't use all the machines, and again, there is going to be some job that actually he depends on, and so on. So you can backtrack, and you can reconstruct a chain of jobs. A chain is it's a sequence of jobs where one depends on the next on the previous one. So you can recover a chain of jobs that covers all the time units where you didn't use all the machines. Okay. Now, the length of any chain is a lower bound on the optimum, because even just to schedule that chain, you'll need opt time units. On the other hand, if you look at the remaining time units, I have used all the machines. That, again, is a lower bound on the optimum. Because even if I throw away all my precedence constraints, that's how much time I need. Okay, and then you add up you cover the whole time horizon of your algorithm, and you add up both of those different time units, and you get that this is at most 2 opt. You can shave off some factor that depends on m and that goes to 0 by just observing that you don't need to double count like the jobs in your chain. if you count a job in the chain, then it's not going to appear again as in that second low bound. But okay. So this is kind of what you can do. Do you have any question? Okay, good. Now this is a factor of 2. And well, if you can get a factor of 2, then the next question is, can I get a factor of 1.9? Well, maybe I can do that. And if the greedy algorithm doesn't do better, then maybe you write down some linear program and you try to do something with that. So that's just the natural approach. And if you sit down 5 minutes and you have to write down some linear program, then probably you will come up with this linear program or with one that looks very similar. Okay. So what are the decisions to make? The decisions that you want to make is like where to schedule every job. So you would probably introduce some decision variable xjt, which is supposed to be 1 if you run that job j at time t. And then there are the usual constraints that you're writing down, like every job has to be scheduled at 1 time unit. For every time unit, at every time you can schedule at most m jobs. And now you kind of, well, how you write down the precedence constraints, maybe you need to think a little bit about that. One option is that you look at every pair ij, so that I has to come before j, and then at every time t, and then you can write down that the fraction with which you have scheduled I between time 1 and t, that has to be at least as large as the fraction of j that you have scheduled between 1 and t plus 1. So something like this. If the x, jt are integral, this is going to do the job. Okay.
So these are unit length jobs?
Unit length jobs, yes. Yeah, if they're not unit length, then things are getting more complicated. We had a talk, that was the rectangles and the height is at most m and so on. Okay. Good. So is this going to be better than the factor of 2? Unfortunately not. It's not really hard to construct some some instance, but we're going to learn a little bit from it. And here we go. Imagine you have jobs which are arranged in blocks. So imagine these are m plus 1 jobs. These are the next m plus 1 jobs. And in one block, the jobs, they all have to finish before you can start with any job in the next block. So if you now look at an integral schedule, you'll need 2 time units to finish one block. But if you now think about what the linear program can do, the linear program essentially needs 1 plus 1 over m time units to fractionally schedule the jobs. So it can run to the same extent, it will run every job in the first block, and then it'll run a little bit of all the jobs in the first block in the second time unit, and then immediately, kind of in the same time unit, start with the next block. And if you stare at this long enough, then you see that actually this is a valid LP solution. And we already see one problem, that even if you have a job I and a job j and they depend on each other, if you look at the LP solution, their support will overlap. So it kind of has to be. So, okay, so there is a gap between 2 time units versus 1 plus 1 over m time units. So this is basically, again, that 2 minus some constant over m time, gap. So also the LP is not going to do better. Okay, so a little bit of bad news. Things kind of get worse in the sense that the question was answered 7 years ago by the usual suspect, that actually under a variant of the unique games conjecture, there is no better than 2 approximation algorithm, even if you assume that the jobs all have unit length. So we are in our setting with unit length jobs. Okay. However, often in scheduling, the number of jobs, it's very large compared to the number of machines, which in theory we like to consider for that case that, well, what happens if the number of my machines is constant and just the number of jobs is unbounded. And in fact, it's in the good old book of Gary and Johnson, there's still the open question whether if you have only 3 machines and the rest of the setting is as I described it, is this an NP-hard problem? And this is still unknown. We're still not seeing the solution in this talk. Yeah, so this is on the original list of, was it 25 open problems? There are now, how many are open? Like 2.5, depending how you count, like graph isomorphism, kind of. But anyway, so there's only very small fractional number of problems open. And there's a nice survey of Schurman and Wöginger, where also this, the question, even whether there is a p-task for this problem with 3 machines, this is listed as a part of problem number 1. Okay, and so the result that we are showing is that actually you kind of can get that p-task, so you can get a 1+epsilon approximation. The way you do it is you take that linear program that I showed you, you throw it in your favorite LP hierarchy, and after some weird number of rounds, you get that down to that 1+epsilon integrality gap. So the number of rounds, it's a little more than quasi-polylogarithmic, like the epsilon and the m kind of appears here in the constant. It's, below the rug as usually. Okay, but morally this is like a Q p-task. It's like a Q p-task. It's a quasi Q p-task. Okay. Anyway, so the running time that you're getting is some almost quasi-polynomial running time. Okay. But okay, so the message is that the linear program, after some strengthening by your favorite LP hierarchy, it can actually do the job. Okay, any questions? Yes.
What is the dependency on M?
Questions one doesn't ask in polite company. No, it's there is an m divided by epsilon squared here, I believe. Yeah. Okay. Fine. Good. Okay, so the goal will be think of the number of machines as being a constant, epsilon as being some small constant, and now we will want to study what the actually the Schiraldi-Adams hierarchy is doing with our linear program. Okay, so if you haven't worked with these LP hierarchies, I'll try to give you a gentle introduction. The general motivation is the following: that you have some linear relaxation for your favorite problem. And the linear relaxation is not good enough. It doesn't do the job that it should be. So imagine like this is like a poor visualization. This is your linear relaxation, K. And this is the convex hull of the integral points. So these black dots, they suggest the integral points. And your linear relaxation is kind of far away. Now what you want to do is you want to make that linear relaxation stronger. One way, like a systematic way, is you introduce some extra variables in a systematic way, and now you can then write down some other system of constraints that's going to involve your original constraints. And if you look back at the projection on the original variables, then the feasible region that you're getting, it's going to be stronger than the one that you had before. It's going to be strictly stronger. Okay, and now these hierarchies, they will have a parameter, and as you increase the parameter, the relaxation gets stronger and stronger, but also the running time that you'll need to solve that hierarchy is gonna blow up. And at the latest, after your number of variables, many iterations, your hierarchy, if you project it down in the original space, it will precisely describe the convex hull of the integer solutions. Okay. So, slightly more concrete, if this is, like in generality, this is your linear relaxation. It's like, this is a polytope. It's going to have all the x so that some linear system of inequalities is satisfied. actually it's going to be important that you assume that the variables are between 0 and 1, which is the case for us. So this is for 0, 1 relaxations. Then systematically what you do is you take every subset of variables of size at most t, and t is going to be that parameter that your hierarchy depends on, and you introduce a new variable y of that index set, and this variable should represent that joint probability that all the variables in capital I are 1 at the same time. So you look at the joint distributions on every subset of I variables. And there's an explicit mechanical way how you can write down a big linear program of size essentially n to the t with that n to the t many variables. And what you will get is that whenever you only look at t many variables, the solution that you have will look like it is actually in the convex hull of integral solutions. So yeah, so this is like a systematic way of getting things stronger. Any question? Okay, so you can see that there is a lot of space on the slide, but I'm not putting. I don't put how you write down those constraints. It's usually if you see it the first time, it's not helpful, and if you have seen it before, then why put it again? I promise you, there is an explicit way, mechanical way, how we can just write down the constraints, and but I want to explain you the properties that we get, and we only use the properties as the black box. Okay, so. Here is kind of the key property that we'll need, and this is called like inducing on one variable, if you look at the literature. Okay, so let's say you have some solution for your T-round Schiraldi-Adams hierarchy, and okay. So and let's imagine there is one variable that you have, one of the original variables, and it's strictly the value of that variable is strictly between 0 and 1. Then what is true is that there will be two other Schiraldi-Adams solutions that I call Z0 and Z1 with the property that Y is a convex combination of those two guys. And Z0 has that variable that we stared at has it 0, and Z1 has that variable that we stared at being 1. And there is an explicit way how you can get these vectors Z0 and Z1. Okay. Now these two other Schiraldi-Adams solutions, they are not going to be feasible for T rounds of Schiraldi-Adams, but they are still feasible for T-1 rounds of Schiraldi-Adams. Okay. Again, there's a mechanical way how we can write this down. It's a little bit, the way how you can think about this is like if you have a probability distribution, there's some event that has probability between 0 and 1. So it's kind of possible that it happens. It's possible that it doesn't happen. Then you can write it as a convex combination of two probability distributions. In one, your event doesn't happen, and the other one, it happens. So this is not a consistent probability distribution, but you can do the same thing here. Okay, so now, again, if you look at the literature, then very often in other algorithms, you will see a sentence like, we want to induce on some variable being 1. And what that actually means is that you have a T-round Schiraldi-Adams solution. Some variable has a value strictly between 0 and 1. And now, if you now imagine you're replacing this vector with this one, then what happens is that suddenly that variable that you have stared at, it becomes 1. Okay, you still have a valid Schiraldi-Adams solution. It's valid for one round less, and that variable is 1. Yeah, so this is a little bit like, if you're a Harry Potter fan, you have your magic wand, and you see some variable being between 0 and 1, then you can say be 1, and suddenly it becomes 1. So Yeah, it's a nice way for your grand application to write it that way. Anyway, okay, so this is a mechanism that we are going to use. There is one technicality that's kind of, I don't want to say trivial, but I hope you'll see what I mean, is that actually if you do this conditioning, if you condition on some variable being 1, if you look at other variables that were not involved, what happens with them? If their value was 0, then the conditioning is not going to change that, right? So if you have a probability distribution and you condition on some event, then some other event, if it had probability 0 before, then it doesn't happen that suddenly the probability goes above 0. Okay? Same here. This is going to be very crucial. It's a little subtle in the algorithm. Okay, good. So these are actually all the properties that we're going to use for Hierarchy atoms. Okay, so now we can come to the actual algorithm. Now we're back to our scheduling problem. We have n jobs with precedence constraints. They have unit time. We have m machines. So we're back to that setting. Okay. Good. So let's say t is our time horizon. Imagine we guess what the optimum time horizon is. We try everything out. And so what we're doing is we split the time horizon into two equal intervals, into two intervals of equal length. Then we split those intervals into intervals of equal length and so on. So we're getting a nice binary family of intervals, partitioning your time horizon. Okay, so that's going to have like log t, which is basically log n, many levels. And okay, so we solve that Hierarchy atoms hierarchy for t rounds, apply to our linear program. T is going to be that weird quasi-polylogarithmic factor. Okay, and now we look at the support of the jobs in that Hierarchy atoms solution. Meaning that there's going to be some job j. If we look at job j, then the Hierarchy atoms solution, it's going to schedule it with some fraction here, with some fraction here, and so on. And the support, it doesn't have to be consecutive. It doesn't have to be an interval. Anyway. And now we imagine the following. Now we, for the time being, we assign the jobs to the smallest interval in our binary family where the whole support fits. And what our algorithm is going to do is then if the whole support was in one of the intervals in that binary family, then our algorithm is going to schedule that job somewhere here, somewhere in that interval. The algorithm will be recursive in the sense that it will start with the small intervals in the binary family. It will schedule all the jobs that are contained in here. And then it will go up, and then it will schedule the jobs that only fit into the larger intervals in that binary decomposition. The intuition is that like these jobs, they have kind of more flexibility to move around, and these are kind of like more restricted. Okay. Good. There's one observation that is going to be important. Let me go back to, I think one can actually see it already from that greedy algorithm that I showed at the very beginning. Right. Okay. So this is that greedy algorithm due to Graham, and I showed the analysis. The Makespan is going to be at most 2 times the optimum. But you can say a little bit more. The Makespan is going to be at most the optimum plus the length of the longest chain. So actually, we did prove that, which obviously at most 2 opt. But if I could, if you would have an instance where the chains are shorter than opt, you would actually get something better. So if all the chains would have length only epsilon times opt, then we wouldn't have to do all that messy business with Hierarchy atoms and so on. Okay, so long chains are a problem. And our algorithm needs to find a way to deal with long chains. Just the very high level idea is that you use the Shirley-Adams solution, use that conditioning mechanism to fix some jobs in long chains. And then you make some progress. We are here. Yes, okay. Any more questions? Okay. Okay, now things are getting a little bit more technical, so please ask if something is unclear. Okay, so this is my binary decomposition of depth like log t or log n, and what I'm doing is I look at the first of those levels, the largest of those intervals, and I look at the first, well, essentially log n square many of those intervals. Think of this as being, morally as being like a big constant. If it was a big constant, yeah, the running time would look nicer, but anyway. Okay, so what I want to do is I want to use this that conditioning mechanism that Shirley-Adams provides me to actually enforce that all the jobs that I had assigned to these log n square many levels, that these don't have any long chain. And I'm going to explain this on the next slide, what I mean with that. Okay, so, but imagine that at least for those, for the set of jobs that are assigned to the top intervals, they don't contain long chains. I can get that. Now let's see. Then what I want to do is I want to create a gap. There are other scheduling algorithms where you do the same kind of game. It's you have some longer jobs, some shorter jobs, then you want to create a gap between them. We're trying something similar here, and the length of the jobs is the same, but it's kind of like how they are spread out in terms of support is going to be different. Okay, so just by some counting argument, I can find a certain number of layers in my decomposition where I don't have too many jobs. And I'll just throw them away. Okay? Okay, now, well, actually, I cannot really throw jobs away. At the end of the day, I do have to schedule them. But I imagine I have a little pile of jobs that I didn't manage to schedule. Then at the very end of the algorithm, I look at my valid schedule with all the other jobs. Now I take the job that I had to throw away. I can find some time unit where, you know, I can insert an extra private time unit and then plug that job in there. So for every one job that I'm throwing away, it's going to cost me an extra one time unit at the end to just fix everything and repair the schedule. Okay, good. So there are some jobs that I'm going to throw away. And now I said that it will be a recursive algorithm. Now what I do is I look at the largest interval below the levels that I've been throwing away. And here, this again looks like the original instance. There is some time horizon, and I look at all the jobs whose support is fully contained in that time horizon. And that again is some separate instance, and I recursively call my algorithm and schedule everything. So they are going to be scheduled recursively somewhere, and I do that like for every of those intervals that are directly below the levels that I've been throwing away. Okay. Good. Now, so there's one remark I should make is that if you okay. So until this step, I have been doing some conditioning on that Shirley-Adams solution. And now I recurse. And what I'm doing is I give a copy of my Shirley-Adams solution after the conditioning. I give a copy to this one, and a copy to this one, and a copy to this one. The point is that what is done afterwards here, the conditioning will be parallel in a potentially inconsistent way. So the point is that, yeah, because I only have some number t of rounds to, you know, only a, yeah. So, and in particular, there's a potential problem. Maybe if I recursively schedule like this sub-instance here, it's like that red job ends up like at the end, this job ends up at the beginning, but maybe I needed some space between those jobs to squeeze in some other jobs that are further up in the decomposition. So it's not clear that this is going to make any sense so far, okay? Okay, so, okay. Because at the very end, I kind of have to show that I can squeeze in those jobs that are in the top levels, where the support is kind of spread out. I have to show that I can squeeze those in between my recursively scheduled jobs that had a shorter support. Okay, so things are a little technical here. Okay, good. There is, yeah. The one thing I want to show you is how we can actually reduce the length of chains. Okay, so let's go back a little bit and imagine. Yeah, okay, imagine here you have billions of jobs. They are all assigned to this very top interval, and in particular, what it means, their support kind of crosses this middle line here. And how could I guarantee you that those billions of jobs, they don't contain a long chain? It may be the case a priori. Okay. But if that happens, I do the following. Okay. So let's say these are my billions of jobs. And in particular, having a long chain means that there is some job where a lot of jobs depend on this guy. So let's say it's this one. So there's some job, and it has some fraction of the time horizon many jobs dependent on him. And the support of all those jobs, it crosses like the same time unit. Now what I can do is, so this job here, it's with some positive fraction, Schiraldi-Adams schedules it in the left part, and with some positive fraction, it schedules it in the right part. So I can now condition on this job here scheduled, let's say, fully in the right part. And if you now imagine what happens to the other jobs that depend on him, they will also be fully scheduled in that right half. The reason is that, this variable, it's like this variable being here is set to 1. And it's still at least a valid LP solution. So it's like all the other variables, all the other jobs that depend on him, they will be scheduled fully in this interval. Okay. Just by having a valid LP solution, and just imagine some variable has been set to 1. Okay, and now you just repeat this game until the dependence of those jobs is below the threshold that you want to have. And you do some counting, which is boring, so we can actually skip that. Okay, but yeah. Okay, so what we can do here is, let me go back to where's a decent picture. It's okay, yeah. We can go back. We can get that all the jobs that still remain and whose support is only contained in those like top intervals, they don't contain long chains. Okay, we could get rid of the long chains. If jobs were in long chains, then actually by conditioning they would have moved down in that decomposition. Okay.
Yes. Right. Why did you go to the right? Why didn't you condition on the left? In that case.
There's no reason why you have to go to the right. You go to one side. You also could have said, let's get one job that has a lot of incoming precedence constraints, and then let's condition him on going to the left. The only problem is he has a lot of outgoing precedence constraints. If you condition him going on the left, that doesn't necessarily have any effect on the rest. So
if you go to the right and it becomes infeasible, what then? Would you just say, oh, that means that?
Well, that it doesn't become infeasible. So the point is that, okay, if the Schiraldi-Adams hierarchy has some variable strictly between 0 and 1, then you know that there is a Hierarchy-Adams solution one round less where the variable is actually 1. So it's in some sense like when you solve Hierarchy-Adams, you have already looked in all directions. It's like all the possible conditionings, you have already tried them out, and they will all be feasible.
Are you trying every possible way to condition the, like, okay, here's how I understand that the algorithm works. Maybe I'm totally wrong. But I thought you pick one long chain, you pick the guy in the middle of the chain, and you say he has to go to the left or the right. Do you try both conditionings?
No, you don't have to try it.
You don't have to try both.
Just you just trust that Hierarchy-Adams, did everything the right way. You don't have to try things out.
No, I mean, conceivably you could solve Hierarchy-Adams, and then you could say that you're going to try every possible conditioning for one, right? You pick number of rounds variables, and then you condition every possible conditioning. This wouldn't cost you extra runtime, but that's not what you're doing.
It's not what we need. We don't have to do that. Okay. Okay. Good. Okay. So we can get rid of long chains at least, yeah, for those like top level jobs. Okay. Good. Okay. So. Okay, but there's the second part of the problem. So the situation may look like this. There are some top-level jobs. These are jobs where the support is really spread out. And there are some bottom-level jobs where the support was contained in like a tiny interval. And we recursively schedule those guys. But there are dependencies between them, potentially. So in particular, some top-level jobs may depend on plenty of those bottom-level jobs, and it may have, like plenty of those bottom-level jobs may depend on him. And we recursively schedule those bottom-level jobs actually independently. So we have actually no guarantee where in this interval, like this guy is going to be scheduled, and we have no guarantee where in this interval this guy is scheduled. Okay. So we're going to be pessimistic, and we will kind of assume the worst case. And the worst case is that if you look at some top-level jobs and you look at all the bottom-level jobs that he depends on, we assume that they are all like scheduled at the very end of their respective intervals, and we call the maximum of those interval ends its release time. And we look at all the bottom-level jobs that depend on J, and the minimum beginning of any interval of these guys, we call that the deadline of J. And now, in some sense, we can cut down the interaction that a top job has with those bottom jobs. We can cut it down to just staring at the release time and the deadline, and this guy just has to be scheduled between the release time and the deadline. Then it's going to satisfy all the precedence constraints between him and the bottom jobs. Okay? Just to reduce the complexity a little bit. Okay, you can already see a potential problem that if this is the support of that Hierarchy-Adams solution, potentially after conditioning, is there might have been some overlap. So some fraction of this job maybe would have been scheduled in that interval, and now we lose that fraction. So we can't use that fraction anymore. Okay. Now, we did create this gap, and if you're wondering how large that gap is, then actually it's the biggest of those bottom intervals. It would fit a quasi-polylogarithmic number of times. No, a polylogarithmic number of times into every of those top intervals. So there is some polylog gap. That's going to be enough. Okay. So we still have to show how can we schedule all the top jobs in the gaps that remain. We're going to do that in two phases. In the first phase, we will generously ignore all the precedence constraints between different top jobs. show that we're not going to lose too much in that phase, and then we will kind of fix the schedule and also respect the precedence constraints among top jobs. Okay. Okay, so, okay, yeah, it's, okay. It's a little bit, okay, now, let's do, yeah. Okay, for a moment, imagine the top, we have to get rid of we have to assign the top jobs. And for the moment, ignore the precedence constraints. So you have unit length jobs. There are some slots left after the recursion. And those unit length jobs, there are some precedence constraints and there are some deadlines. Like algorithmically, how could you do that? There are some scheduling experts in the first row.
It's a unit thing. It's just greedy. It's just matching, right?
Either matching or greedy. Yes, both works. Okay, yes, yes. So it's it's a bipartite matching thing, or if you do everything with earliest deadline first, probably you can do other greedy type algorithms. It's a nice polynomial problem. Yes. Okay. Okay. In particular, well, okay. In particular, the following. You have this Shirali-Adams solution, and the Shirali-Adams solution, in particular, it's a fractional solution. It will induce a fractional matching, which you can nicely use if you want to have a matching-based argument. There is one problem, is that you can think about this as follows. If you have your jobs on this side, if you like set up that bipartite matching problem, and there are some slots. There are some slots on the right side, and like somewhere here is some job J, and it's possible that it's going to be assigned to some slots. So it has some neighborhood, and it's like you have this variable, like you have this Shirali-Adams solution. It's going to tell you that, okay, there's some fraction. With some fraction, it goes to some time unit t, and you know that this is essentially, it's a fractional matching. So you know that actually there is a way of scheduling the top jobs. There's some problem that actually we are going to cut off some of the slots at the end, these ones here. So we're kind of losing something in that fractional matching. There's kind of a variant of Holt's theorem that tells you, like, if you have a perfect matching, now you're cutting off parts of your neighborhood, like how many left-hand side jobs can you not assign? That's essentially by the worst by how much like the neighborhoods shrink. And okay, so you can apply that little theorem. So you can look at some subset of your jobs, and you can see by how much would the neighborhood shrink. Now you can observe that actually, since these, like all your top jobs, they contain one of those like big interval endings and beginnings. So you can you're only losing the slots contained in one tiny interval per big interval. Well, at most 2 tiny intervals per big interval, but there are like polylogarithmically many tiny intervals in every big interval. So that means you're only losing a 1/polylog fraction. Okay? That was a little bit fast, but it's not a too hard thing, just staring long enough at Holt's theorem and counting like how many jobs you could not assign. Okay. Okay, so that means there is a very limited loss. It's just a polylog fraction of all my jobs that I'm losing, at least if I'm allowed to ignore the precedence constraints. Okay. Yeah. Okay, so now I kind of have to fix that. And so this is the last thing that I have to show. This is actually going to be the last slide with some action on it. So this is the problem that I have to solve. There are some jobs now with precedence constraints. So these are my top jobs. They have precedence constraints. They're going to have, there's some chain length that I can control. They have release times, deadlines, and there is some remaining capacity curve that's kind of left after I recursively scheduled all the bottom jobs. Okay, and I know that, well, I have enough slots so that if I wouldn't have precedence constraints, I could, schedule all the jobs. Okay. So, let's go back to the question that, okay, I have unit length jobs, release times, deadlines. Without the precedence constraints, I could use matchings or I could use greedy. What type of greedy algorithm? This EDF, earliest deadline first. Very well-known policy for the scheduling people in the audience, I guess. So what you're doing is that if you have jobs and they have some deadline, then you just run them, and you always take the jobs that have the latest deadline. And for the people in the audience who are currently writing tenure letters, that's kind of probably how you schedule your letters as well. Okay, so the good news is that it's a polynomial time algorithm, and it's an optimum policy if you don't have precedence constraints. Just from the intuition, what do you think happens if you have precedence constraints, but I can guarantee you that the chains in your precedence set are short? It's probably not an optimum policy anymore, but the shorter the chains, the kind of more closer to being optimal it gets, right? And that intuition is right, and it's not really hard to prove. But now it's going to be crucial that we can actually get that maximum chain length C. It's going to be a fraction of my jobs, and I can make that fraction as small as I like, and I pay with that just by losing Shirley-Adams rounds. Okay, so I can make that a maximum chain length as small as possible, and now I just run earliest deadline first. Okay, so what I do is, to be precise, it's the following. So I start at the first time unit, and I take the job with a minimum deadline, and I just schedule it. If it ever happens that I don't manage to finish a job in time, then I just throw it away. Then at the end of the day, I count how high my pile of discarded jobs is. Okay. The analysis is going to be very similar to that classical analysis that you can find in any scheduling book. There they prove that EDF is optimal. Here we prove that EDF is almost optimal, and the almost depends on the length of your chains. Okay, so now let's say you run earliest deadline first, and it happens that there's going to be some time interval where you have to discard a ton of jobs. A ton, let's say, is K. Okay, and now you can backtrack. And you can go to the last of those intervals where you had a lot of idle time. A lot of idle time for me means more than the length of the longest chain many idle times. Okay, so in particular, every interval between did not have had at most C many idle times. And now you can do some reasoning. And the reasoning is as follows. It's not possible that you have a job somewhere here that had a release time that was released here. Because that guy, I could have scheduled him here because I have enough idle times, right? Okay, so if you have, the point is if between the release time of a job and the time that it was either finished or discarded, if you have more than C many idle times, you kind of get a contradiction because then you would have scheduled that guy earlier because the length of the longest chain is C. It's kind of an argument that's very similar to what I showed you like on the second slide in the analysis for the greedy algorithm. Anyway, so you get some kind of contradiction because you know that the number of those intervals times C actually cannot exceed K, and then you get some bound on K. And that's going to be enough. I'm sorry that things are going to be a little bit messy. Those numbers aren't really important. You do the accounting, but things are going to work out smoothly. OK. That's kind of the end of the technical part. There are some nice open problems. Now it's one open problem less, actually. The number of rounds that I needed, it was like log n to the log n. And there was a recent improvement by Shashwat. You can actually get things down to polylog many rounds. That gives you an actual quasi-polynomial running time by essentially doing the recursion in a smarter way. It's still open whether you could use just some constant depending on epsilon and m, many Shirley-Adams rounds. Probably if you want to get that, your algorithm has to be very different. It's kind of whenever you recurse, you probably have to lose a log n somewhere. Finally, a nice open problem is what happens if your jobs are not unit length jobs? What if they have arbitrary processing times? Some of the arguments still work, some don't. And in particular, if you know that you have enough slots for your jobs, that's not enough to argue that you can actually schedule all your jobs if the running times are different. But anyway, I think I'm finishing 5 minutes early, but it's.
Questions?
Can you go back to in terms of when you say conditioning, what exactly do you do in the sense that algorithmically, which jobs do you pick in the top? You recurse on you first choose that middle layers and discard those jobs. You recurse on the
Bottom,
but you do the conditioning before that? Or?
Yes, it's important. Yes, you first do the conditioning, then you throw away like some middle layer, the jobs in some middle layer, and then you do the recursion.
So when you say you condition, when you say you condition, you mean on which jobs? On the top level jobs?
You would, yes. It's like if this number is too big for you, if like there's like a too long chain here, then you would like condition on this guy be going, let's say, to the right side. Yes.
So you look at the jobs, you look at the chain length of those jobs, and then condition.
Yes.
So how much of the, I guess by now, only quasi-polynomial is driven by actually trying to get a scheme, rather than, let's say, I give you, I have 1,000 machines, and I want to get 1.99. Is that something that there's enough technology there to just actually make out and out polynomial?
Getting a 1.99 in polynomial time, it's not coming out of the algorithm, no. That would require some extra thoughts. Right.
Are there integrality gaps known for Shirley-Adams with a constant number of rounds? Let's say.
I'm not aware of any, and I haven't really tried.
Any other questions? If not, let's thank Thomas again.